now we'll discuss polygons, convex as well as concave, because the figures may involve concave polygons even though the term may not be mentioned as such. So polygons are n-sided closed figures. So what do we mean by that? Let's say this is what we have. This is a polygon. It has 5 sides. So 1, 2, 3, 4, and 5. So it's a 5-sided closed figure. I mean, just ignore this tiny little thing over here, of course. Yeah. So this is a 5-sided closed figure. Similarly, we can have a polygon of any number of sides. For example, let's say this is also a polygon. Of course, closed figure, n-sided. Then, for that matter, something like this is also a polygon. Again, it's an n-sided closed figure. So, but this is a convex polygon and this is a concave polygon. And we'll discuss about what these are. So, no worries. First of all, we'll discuss what a convex polygon is. Okay, no, first let's discuss any side of a polygon is less than the sum of all other sides. Now, this is intuitive. This is just like, do you remember what we discussed when we were doing triangles? We said that any one side of a triangle must be smaller than the sum of the other two sides. Now, the logic over here is also exactly the same. So let's say I have a line of length 10 centimeters. And say I have 3 more sides. One is 2 centimeters, another is 3 centimeters, let's say, and another is 5 centimeters. So then this is 2, this is 3, and this is 5. So now if I want to make a polygon with these 4 sides, think about it. Even if I straighten out the 2, the 3, and the 5 all in a line, then I'll be able to make it equal to 10, right? But I can't make a polygon like this, right? I can't join these 4 sides to make a polygon. This side, this must be smaller than 10. Only then, like for example, over here, now this must be less than 10, isn't it? If it is, this has to be less than 10. If it is 10, then I'll have to lay down my sides of 2, 3, and 5 in a straight line. But then I can't make a closed figure with that. So that is why, just like in a triangle, in a polygon as well, any side of a polygon is less than the sum of all other sides. Okay, now let's discuss what are convex polygons. As we said that there are 2 types of polygons, convex and concave, and usually we deal with convex polygons. So the triangles and the squares and rectangles and the pentagons, the octagons, they're all convex polygons, the ones that we come across usually. We'll talk about concave as well a little while later. So in convex polygons, each internal angle is less than 180 degrees and the sum of all external angles is 360 degrees. Okay, so let's draw, let's say we draw a triangle. Yeah, all right. So here is our triangle. Let's say this is our point S. We have to draw a closed figure. A polygon is a closed figure, right? So let's say I'm standing at this point S and say I start walking in this direction, right? And I had to walk in this direction, but I took a detour. I let's say turn by an angle of say 130 degrees, right? Now I start walking in this direction and I would have continued walking. Look, now I'm walking in this direction, right? And I would have continued walking, but then again, I took a detour and I turned by an angle of, let's say, 100 degrees. I'm taking these turns in anti-clockwise direction, right? So this is where I started from. Then I kept going straight, but then I took a detour and I turned by 130, then I turned by 100. Now I'm walking here, right? But then I took a detour over here once again. And here I turn by another 130 degrees. Okay, why am I sure that I turn by another 130 degrees over here? Then now I come back to my original point, which is S. Since I started at S, and then I took some turns along the way and I came back to S over here. The total angle, this is going to be 360 degrees. We know that angle around a point is 360 degrees. So when I go around in the circle, the total angle that I would have taken is 360 degrees. I am kind of going around in a circle in case it's a closed figure, right? It doesn't matter. Even if I'm going in a straight line for a while, I'm turning this angle, I'm turning this angle, and I'm turning this angle. In a circle, I'm just turning at every point. My angle is changing at every point. Here, I'm changing it in steps. First, I changed by 130, then by 100, and then again by 130. But overall angle change, in case I start from a point and come back to it, that is going to be 360 degrees. So that is why the sum of all my external angles, these are called my external angles. I was going to go in this straight line right here, but I turned and I changed my direction. So this angle, the one that I changed my direction with, this is the external angle, right? So the sum of all the external angles will add up to be 360 degrees. Of course, now what will be the internal angle over here? Since I'm turning by 130 degrees over here, so, and this is a straight angle, right? And I'm turning by 130, that means this is my 50 degrees, the internal angle here. Then here I turn by 100 degrees, so that means the remaining angle is 80 degrees. And I turn by 130 degrees over here, so my remaining angle over here is also 50 degrees. And of course, as we know that the internal angles of a triangle, they add up to 180, and they do, right? These are all 180 now. What happens when we have a rectangle? So I'm starting from a point S. Then, for example, you know what? I was supposed to go straight in a line, but what did I do? I turned. By how much? I turned by a 90-degree angle. Again, this is, I turned in this direction. It's an anti-clockwise angle of 90 degrees. Then again, I was supposed to go on and on in a straight line, but I turned yet again. By how much? Again, I turned by 90 degrees. So in this direction, by 90 degrees. Now, I was supposed to go straight in a straight line, but then again, I turned and I, by the 90-degree angle, let's say. And then over here, I was supposed to go in a straight line, but then again, I turned by another 90 degrees angle. Now, this is not a surprise. So now I came back to S. This is not a surprise that I turned 90 degree. If I was turning only 90-degree angles, then I had to turn 4 times. Why? Because the total external angle must be 360 degrees, because I started from a point and came back to it. But then, since over here I had a 90-degree angle, here all the internal angles, 90, 90, 90 and 90, they add up to 360 degrees. Look, I took smaller steps now, smaller turns here now. So I had to take more turns. And the internal angle then is all adds up. There are 4 of these 90-degree internal angles, and they added up to be 360 degrees. Here, the internal angles added up to be 180 degrees. Now, think about what happens when we take 5 such steps. We'll take a look at that also. So, say I start from here. This is my point S. I start from here. And even though I was supposed to go straight down the line, but I took a turn. Let's say. Then I again took a turn. Now the angle that I'm turning over here, of course I can turn any angle, but let's say I'm turning a smaller angle now, not 90-degree angle. Now I'm turning a 72-degree angle, for example. Then again I turn a 72-degree angle. Yeah, then again I turn a 72-degree angle, and then again I turn a 72-degree angle. Of course, since I'm turning 5 times and I'm assuming that all these are equal, so I'm just assuming, let's say that I'm turning by an equal angle every time, though it's not necessary, of course. So all these are 72 degrees. The total sum has to be 360 of the external angles, as we discussed. All these angles that I'm turning, they have to be 72 degrees. The total sum has to be 360 degrees for them. Now, what about the internal angles? So this is 108 degrees. This is 108 degrees. This is 108 degrees. Do you see that now I have 5 internal angles, each of them 108 degrees, right? So that is a total angle of 540 degrees inside. Right? So the sum of all the internal angles over here turns out to be 540 degrees. Now it's even more than before. So when we take smaller angle turns, that means the external angles are smaller, we turn more number of times, and that is why the number of internal angles that we get keeps increasing, and in the degrees and the number as well. So overall, the sum of our internal angles keeps increasing. Now, normally the way I like to calculate the sum of all internal angles of an n-sided polygon is that, for example, if I have 10 sides, I would say that then that means the external angle is 360 by 10. If all the external angles are equal, then I would say that the external angle is 360 by 10, which is equal to 36 degrees. And every internal angle is going to be 180 minus 36 degrees, because the internal angle and the external angle, they are a straight angle, right? They form a straight line. Together they have to add up to 180 degrees. So that is why then I say that then each internal angle must be 144 degrees, right? All right. Now, if I have to sum all the internal angles, I would say then that must be 144 into 10. Because I have 10 sides, so I have 10 internal angles. So the sum of all internal angles will be 1440. Of course, if a polygon with 10 sides is called a decagon, and in case all the angles of the decagon are equal, then every angle will be 144. We're talking about internal angles here. But if in case the angles are different, they could be, but the sum would still be 1440 degrees of all the angles. Now, there is another formula that we use to find the sum of all interior angles, all internal angles. And what is that? That is n minus 2 into 180. How do we get that? Look, we have a pentagon over here. Let's say if I split the pentagon into triangles, now I am able to make 3 triangles. So even though I had 5 sides, I'm able to make 3 triangles. And of course, the internal sum of all these 3 triangles will be 180 degrees. So that means this angle, right? Then this angle, then this angle, this will add up to 180 degrees. Then look at this angle and this angle and this angle, they'll add up to 180 degrees. And then we are left with this angle, then this angle, and this one. They'll also all add up to 180 degrees. So now we have, and in all these green, the red, and the black together, they form all the internal angles of the pentagon. So that is why all the internal angles of the pentagon will add up to 180 plus 180 plus 180. That is 180 into n minus 2, because a 5-sided figure gives us 3 triangles inside. Now look at this. For example, if I make a 6-sided figure, that's a hexagon, right? Let's say I make a 6-sided figure. Now, how many triangles can I make? Take any vertex. This vertex I cannot link to this vertex because it's already linked to this vertex, right? This vertex and this vertex, because it's a side. So I can link to this vertex to make a triangle. I can link to this vertex to make a triangle, and I can link to this vertex to make a triangle. Again, I can't link to this one. Why? Because it makes a side with this. So then let's say this vertex A, it makes triangles with not two of the vertices, with not with this and not with this, but with all the other vertices, and that is why we get n minus 2 triangles. So a six-sided figure makes 1, 2, 3, and 4. That is 4 triangles. And that is why the sum of all the internal angles will be n minus 2 into 180 degrees. Now, in case they told me that each internal angle is equal, I could just divide this entire sum of all the internal angles by n, because an n-sided figure will have n internal angles. And if all of them were equal, I would just divide the sum by n. Now, this is exactly the same as what we discussed over here, where we said that each internal angle, if they are equal, will be equal to 180 minus 360 by n. What is this 360 by n? This was the external angle. We said since sum of all external angles 360 degrees and there are n sides, that means we have turned n times. So 360 by n is each external angle. And when we subtract it from 180, because internal and external angles, they make a straight line. So then we'll get the measure of each internal angle, right? So this and this are equivalent. Okay, now the sum of distinct diagonals of an n-sided polygon will be the number of distinct diagonals. Okay, so in fact, how many diagonals can we make? All right, so look, we discussed a hexagon over here. We said that the hexagon has 6 sides, right? And we took A as one of the vertices there. So we can say A, B, C, D, E, and F are the 6 vertices of the hexagon. So we know that A cannot make a diagonal with B because AB make a side, and A cannot make a diagonal with F because AF make a side. So A makes a diagonal with C, with D, and with E, right? So A joins with C, D, and E. Now, what about B? B cannot make a diagonal with A and C, but it can make a diagonal with D, and with E, and with F. What about C? It cannot make a diagonal with B and D, but it can make with A. It's already made it with A. It can make it with C, E, and F as well. D can make another diagonal with F as well. And that's it. So now we've got all the diagonals. So the number of distinct diagonals of an n-sided polygon. Look, so how did we get? We said that there are n vertices. Now we picked up each vertex, and for example, we picked up A, and we said that it can make a diagonal with C, D, and E. It cannot make a diagonal with B, A, and F. So it cannot. Why? Because B and F are right next to it, and A is itself. So out of the n vertices, it can make a diagonal with n minus 3 vertices, right? And A could make a diagonal with n minus 3 vertices. So this will be the case for all the vertices. B can make a diagonal with n minus 3 vertices. It cannot make a diagonal with A, B, and C, but it can with the others. Same for C, same for D, same for E, and same for F. So the number of diagonals will be n minus 3 into n. But then note here that we are counting every diagonal twice. So when I say that A makes a diagonal with C, I'm also counting it as C is making a diagonal with A. So I'm counting every diagonal twice, so I divide this by 2. This is the number of diagonals that I get when I have an n-sided polygon. N into n minus 3 divided by 2, right? Or we could use combinatorics over here. We say we have n vertices. So we pick any 2 vertices. Let's say we've picked A and D, NC2. We can pick any 2 vertices out of n vertices in NC2 ways. So we have picked up, let's say, A and E, A and C, A and D, right? And we have made diagonals out of it. But remember, we would also pick up A and B. And that we are not allowed to because that is a side. We would also pick up A and F. We are not allowed to because that is a side. We'll also pick up D and E. Again, that is a side. So these we need to subtract. We need to subtract n out of it. Why? Because it's an n-sided polygon. So we subtract n out of it. Hence, the number of distinct diagonals of an n-sided polygon will be nc2 minus n. And as we just discussed, it can also be given as n minus 3 upon 2. Of course, nc2 minus n gives you n minus 3 upon 2 upon simplification as well. Of course, they're both the same. To get the measure of an internal angle of a regular polygon, just divide 360 by n, the number of sides, to get the measure of the external angle. Then from 180, subtract the external angle to get the internal angle. So this way you get the measures of both the angles. Yeah.